with this, if you're ready, I think we are all ready, and so we're very happy to have one of our own, a professor here at Ireland, who is going to give the next lecture, Peter Sunderland, and Peter is going to talk about basically two topics, soot and radiation. And Peter, the floor is yours.
Thank you, Arnaud. It's a pleasure to be here, an honor to speak with everybody. And I should say I've had good luck with summer schools. At the summer school on hydrogen safety in Belfast is where I met my wife. And we're still married. We have a 9-year-old, a 10-year-old. And so I'm glad to be here. So as Arnaud said, this is two separate topics, two disparate topics, soot and radiation. And they're big topics. So it's a lot to cover in 90 minutes, but I'll try to give you an overview of each, kind of the basics like anybody in fire should understand about soot and about radiation. And there is a lot of overlap as well, but it's sort of a talk in two halves, first half on soot, second half on radiation. If you were to pick two canonical images of, what does soot look like, this image on the left gives you a good idea. This is a transmission electron microscopy measurement from a building just next door, taken by a student, Paul Anderson, who's been for some of the summer school. And on the right is a large bonfire, a warming fire. This is a fire in Canada that actually caused a couple of fatalities, not because of the bonfire, but because somebody threw a bucket of liquid fuel into it. So again, the left you see a particle of soot, which is a view most of us don't normally see, and on the right, a very strongly radiating fire. I want to acknowledge past students, Catherine Allen, Paul Anderson, Jose Castillo, Haiqing Guo, Vivian Lecruz, Li-Ming Li, Jignesh Mon. Funding from NASA, NIST, and NSF is presented in some of these results. So what is soot? This is a picture of a truck we've all been behind, bellowing out black smoke. And all of us, our instinct is, hold your breath. If you're out running or biking, try not to breathe that stuff. That's the right instinct. This is the worst kind of smoke to breathe into your lungs. Some say it's perhaps as bad as breathing asbestos. So particles that are similar to the size of asbestos. They're not as sharp and pointy, but they're small enough to get deep into the alveoli, into your lungs. They can cross over into your bloodstream. Then, of course, they accumulate in your heart, your brain, your liver. So it's, of all the types of smoke, it's one of the most toxic types. This is a diesel engine. That's why it's producing a lot of soot. Luckily, the engines are getting better. The filtration technology is getting better, so we're seeing less of that. But soot still gets produced from a lot of wildland fires. So let's start with the definition. As Guillermo Rain explained previously, smoldering doesn't produce any soot. Soot can only be produced by flaming fires. So there has to be a flame for there to be soot. It's basically a gas phase phenomenon where the carbon from the fuel gets converted into solid carbon. It's good to be aware of some other terms that get used that are kind of related but somewhat different. First one is pyrogenic carbon. This includes soot as one of the types of pyrogenic carbon, pyro being fire, but black carbon is also a synonym, but char and biochar also fall under this category. Let's define those. Char, again, Guillermo Rain was talking a lot about char. This is the solid pyrogenic carbonaceous materials from incomplete combustion. What's left after the smolder goes out prematurely. And biochar then is often talked about as a form of char that's intentionally made. And this is used for carbon sequestration and soil amendment. So again, today, the first topic is on soot. So we're not looking at char and biochar, although sometimes these do go into the smoke of a wildland fire. I'm interested in the soot that's formed in the gas phase. Here are a couple of images of soot. So this candle flame on the left is at the smoke point. We actually produced it here by adjusting the wick until you can see the ears on the flame are equally as long as the center of the flames, the candle flame at the smoke point. And the two main colors you see here are blue at the base, it's the hottest part of the flame, and yellow, which is the soot. So that's a macroscopic view of soot that's not going out as smoke, as black smoke. And on the right then, a large soot particle. This is taken again by Paul Anderson in the building next door, where you can see the structure of soot is kind of like a pearl necklace. The leading models of soot morphology say that these are spherical particles, roughly the same size. You can see lots of spherical particles in this aggregate, and they're clumped together, kind of like a pearl necklace where there's one size that describes all the individual spherical particles in this soot aggregate. And this image probably has, 500 individual spherical particles. These are two important views of soot. So let's differentiate again now in definitions that soot isn't the same thing as smoke necessarily. Lots of smoke has soot in it, but there's plenty of smoke that doesn't have soot in it. For example, cigarette smoke. We call that cigarette smoke. It is smoke, but it's blue. It's not black like soot smoke. And those blue particles, they're liquids. They're not solids. So it contains, it's a hydrocarbon. There are tars and oils. They look blue, but that's not soot. Now, I'm not encouraging anyone to smoke, but if you're going to breathe one of these, I'd rather have you breathe the blue smoke. Incense and cigarette smoke, smoldering smoke, isn't as bad for you. Lungs can flush that out. It doesn't go as deep and cross into your liver, heart, and brain. And then on the right here are some water droplets and ash. So large fires can make water droplets and spew plenty of ash. And these are white or gray. So just from looking at the smoke from a fire, lots of times you can identify these three main types. The soot and char, which are black, these are the World Trade Center fires. Oily droplets that are blue, and the water droplets and ash that are white. Bless you. So there are huge health and environmental impacts. This was the front page of the New York Times talking about the number of deaths from soot. Just in the United States, they're estimating 60,000 deaths a year. Now, they use the term soot loosely here, and it's used to include things like dust that gets picked up in a dust storm, ash, volcanic ash, any kind of solid aerosol is often viewed by the public health people to be soot. Now, soot's an important part of that, but lots of these other particulates contribute to that 60,000 deaths a year, but it's tremendous. It's a tremendous health impact. And from wildland fires, the damages from downwind from the soot and the other toxins that are released in the plume often exceed the property and loss of life damages and firefighting costs of the actual fire. And then the article on the right there from Nature, this talks about the dark side of aerosols, especially the global warming, and although there's a lot of uncertainties, this claims that soot deposits, especially on ice, are the second greatest cause of global warming after carbon dioxide. So the economic costs of soot are really tremendous for both health and for the climate. In fires, this is the same image from Canada, the Hickory record, 2013. Keep in mind, I think everybody gets this drilled into them in our department, that most people who die in fires don't die from burning to death, although that's a horrible way to go, and it does kill many people, but mostly from smoke inhalation, and that specifically often from the carbon monoxide. Of course, if you can measure the soot emission from flames, that correlates directly with carbon monoxide emission. Sometimes it's easier to measure soot emission than carbon monoxide emission, and these two are correlated. Of course, radiation is the dominant mode of heat transfer in many fires, not all fires, as we heard from Sarah McAllister today and almost everybody on this program. There's competition between convection and radiation and fire spread, but radiation, of course, is important. And often in fires, the radiation is dominated by the soot. So if you understand how soot behaves radiometrically, you can understand the radiation from your fire. And finally, it's important to understand how soot behaves in fires from numerical models, and lots of the leading numerical models include soot models. Now, Arnaud mentioned yesterday that including the fully detailed soot models is onerous and not possible in his latest codes, so we have to respect that, but in some sense still, he does need to account for the soot with a very simple model in his codes. So, to summarize some of those things, let's look at the benefits and hazards of soot. You don't want to come out of this today and say, boy, soot's bad. Soot isn't always bad. So let's start with the benefits. If you're making a boiler, like lots of coal-fired boilers, or even the boiler in my house, natural gas boiler, it's nice to have radiation. That's a great way to transfer heat from the gas into the liquid to heat your water. It's excellent for rubber additive. It's one of the first nanotechnologies for making additives in our tires, on our bicycles and cars. It's used for printer toner, it's the paper that we print, pigments for paints. It's used even for lubrication, filtration, and of course candles. Candles are effective and have been used for hundreds of years because of the soot that produces the light that you can read by. So there are plenty of benefits. I haven't been able to list them all, but there are lots of benefits of soot, and there are lots of combustion processes where you want to produce soot. And you usually don't want to release that into the atmosphere. So on the other side, the hazard side, it's longer, and I had to shorten this list to make it even fit on the same page as the benefit side. So starting with the United States, estimated 60,000 deaths annually. It's cytotoxic, so it kills cells. If you put a cell in a petri dish with soot, it will kill the cells. It's carcinogenic. All soot particles are formed with lots of PAHs, things like benzene that are known carcinogens. So that soot particle that gets deep into your lungs does carry with it carcinogens. Of course, carbon monoxide emissions, as I mentioned, is associated with it. Climate change, it affects the fire spread, fire obscuration. It's difficult to fight a fire if you don't know where it is. Property damage, and radiation in engines, radiation and fouling. If you have radiation in a boiler, that's good, right? If you're burning coal and want to boil water, that's good. If you have radiation in a diesel engine, that's bad. That's heat that's going to be lost to the surroundings and need to be cooled and go right out into the radiator. Then let me close this slide with a quote from Wang and Chung, a recent review from Progress Energy Combustion Science. Soot formation is one of the most complex phenomena in combustion, involving complicated interactions between combustion chemistry, fluids, heat and mass transport, particle dynamics, so that despite decades of active research, many gaps still remain in our understanding of soot. And you see this kind of claim from lots of researchers. Maybe it's the introduction and right out of our proposal where he said, let's, give me more money to study soot. There's still a lot we don't know here. You see this, I think from lots of people in the sciences, turbulence people and radiation people will say the same thing. This is one of our hardest problems. Wang and Chung is a nice paper, and they go on to look at some statistics. They say that in combustion and flame titles and abstracts, that the word soot appears in 10% of the papers. So it's still a tremendous field of research. As I'll show, a lot of the best models that we have and the best measurements for soot were taken sometimes 50 years ago. So they're advancing around the edges, but the big picture of soot is, I think, fairly well understood and mapped out. And of course, there's still plenty of unsolved problems there. So let's look at the soot chemistry briefly. There's so many different versions of this schematic that talk about how soot burns. I don't have any videos today, but I do have a lighter. And, we've all looked at these lighters and studied how the flames burn. And what's happening in here is complex processes that are shown on the screen. So you start with the fuel and oxidizer at the base. In this case, this is a butane lighter, and it's air. It's a diffusion flame. At the base, the flame is blue. Again, that's the hottest part. Temperatures around 2200 kelvins, 2000 kelvins. Fuel and the oxidizer. And by the way, this picture of the flame and the nice graphics that goes with it comes from Hope Mickelson out of University of Colorado. So the first thing happens is in this blue flame, it's a diffusion flame, so the oxidizer and the fuel are diffusing toward each other. You have a reaction at the stoichiometric location, and you start with the fuel and oxidizer. For example, it could be heptane and air, or in the case of this flame, butane and air. And this pyrolyzes, so the air becomes OH, hydroxyl radical, O atom. The fuel becomes hydrogen atom, CH, CH2, and importantly, acetylene. But there's a lot of pyrolysis that goes on first. These molecules heat up and they pyrolyze down to very small molecules. Later on, you're going to see that you form soot. And what's amazing here is that if you're burning something like tar or oil, very heavy molecular weights, the first step they do, and it seems kind of crazy going against Mother Nature, is they break down into these very small molecules, molecular weights of 1 and 16, and then they build back up into soot molecules with 1 million carbon atoms in it. It's just remarkable that happens. But the first step at these high temperatures is that you get the pyrolysis and you have these radicals in very small molecules. Then the next step in soot formation is to form PAHs, polyaromatic hydrocarbons. These are ring structures starting with benzene that group together, and they start to make graphitic layers, and they make fullerenes, all kinds of aromatic carbon structures. And this is the soot precursors. This is the stuff that's in cigarette smoke, these PAHs and oils that look blue. They make droplets. They're liquids in the flame. I've seen them in the electron microscope, and they do look round. They're not solid, but they're liquid-like. And these then can start to nucleate. So these polyaromatic hydrocarbons, they're heavy, so they're not bouncing around like a hydrogen atom, but they're still moving by Brownian motion. They collide and they coalesce, and they form they start to nucleate these particles. So these particles, typically in the nucleation stage, have diameters of 1 to 6 nanometers. That's why we look at them in electron microscopes. And they have lots of different names and the nomenclature that's used for this. So it's a nucleation step in soot. They're called nascent particles or nano-organic carbon. There are two different main structures with the graphitic layers. They can be disordered, especially in lean combustion. You see disordered layers of carbon, or they can be stacked up like graphite if it's a rich flame. They're liquid-like, they're oil-like. The carbon-hydrogen number ratio is between 1 and 2, and again, the diameters are around 1 nanometer. After this, what happens, the next step after nucleation is growth, soot growth, where you dehydrogenize. So the hydrogen gets pulled off, and the carbon-to-hydrogen ratio increases dramatically. So during the growth phase, you go from around a 2 carbon-hydrogen ratio to 10 or 20. So now it really looks like almost all carbon, at least by mass, but even by number, almost all carbon. And this is the process of growth. The growth process is dominated by acetylene colliding with the soot surface and attaching to the soot surface and adding to the mass of the soot. These primary particles then, for some reason, they stop growing around 15 nanometers. I don't think anybody's really figured out why that is. And then those 50 nanometer particles could be 30 nanometers, but for some reason they're always in this tight range. They come together like the pearl necklace and become the aggregates, like I showed earlier. And that's the aggregation step. And then finally, if it's a good flame, usually you want everything to oxidize, like a candle flame or this butane lighter flame. You have full oxidation, and then even though you're making a lot of soot in this flame, you can emit only carbon as carbon dioxide. So in the next few slides, I'll go over these individual steps and talk about something I think all fire scientists should understand about the soot processes. So the first step is nucleation, forming these tarry and oily particles low in the flame. And the best surrogate for the model for this, the mathematical model for this, is looking at the temperature and the acetylene concentration. And if you know the temperature and you know the acetylene concentration, you can simply then plug that into one of these models. They're all kind of similar. They all have an activation energy depending on the temperature, and get the rate of nucleation. So it tells you basically the mass formed of soot particles per time per volume. And the three leading ones, Moss, Lung, and Fairweather, I think they're all pretty good. It's a relatively easy model because the nucleation stage, these are spherical particles, so surface area isn't as important. And it really depends only on the acetylene of concentration. It's the concentration of acetylene. They're all tied back to acetylene. So there you have the nucleation step. And the next step, there's the growth step. And this is when you have acetylene attaching onto the surface of the soot particles. Now, the simplest model is from Lung et al., and it's the most widely used, but unfortunately, it's one of the worst models because in the images from the electron microscope that I've shown so far, you see that the soot aggregates are modeled as spheres touching at a point. But the Lung model, it takes that whole soot aggregate and clumps it in and says, what's the equivalent sphere? And because the area is so important for soot formation, the rate of soot growth is proportional to the area, that approximation that a soot aggregate is a sphere is very inaccurate. And so they've adjusted the other parameters in this Lung model to account for that, to get the growth rates up to where they need to be, but it's not a rigorous model. So the improved model is from Franklek and Wang. Hai Wang at Stanford, really, and Franklek at Berkeley are the two, I think, leading living researchers on soot chemistry. They wrote this HECA mechanism, hydrogen abstraction carbon addition mechanism for soot. And what they said is that the first step is that you have to activate the soot surface by removing a hydrogen atom. So that's the HA of the HECA word. Hydrogen abstraction is where a hydrogen atom collides with a soot particle and pulls off another hydrogen atom, makes H2, and now you have an active site on the soot particle. So the soot is given a little black dot to indicate that now it's a radicalized soot, and it's ready to have the growth process. And that step's reversible in the second step. But now, when you have this active site on the soot surface, it can receive an acetylene molecule and cause growth. And when it grows, then you add a molar mass of 24 to the soot particle. So this is a system of growth that depends on the acetylene concentration and the temperature, but it also depends on the hydrogen atom concentration, because hydrogen atom is an essential species for soot growth. Now, since this model came out in 1991, it's still the leading model, and one thing you're going to notice is that a lot of the best stuff in soot, best measurements and models were written a long time ago, and there's been a lot of debate, a lot of people coming out and saying, oh, acetylene can't do all the work of forming all this soot. It's got to be going through PAH. And that may be true. It may be that the acetylene actually forms these ring structures that then contribute to the growth. But it's baked into the models that acetylene can be a surrogate for the PAHs, and things correlate nicely with acetylene concentration using the HECA mechanism. And then the next step here, and maybe the most complicated, is what's the size of the primary particles for the soot? So this is really part of the chemistry, because the particle size depends on the nucleation rate and the growth rates. And let me start first with the image here on the right, where this is, again, Hai Wang at Stanford, showing the size of primary particles versus their number concentration. And you can see that in general, it's bimodal. So you have a lot of particles that are very small here in the 1 to 10 nanometer range, and then a lot of particles that are in the range of 60 to 100 nanometers. And so it's a bimodal distribution. What's happening is that the growth and the nucleation aren't quite as simple as the first picture I showed. They actually overlap in the flame. So the early soot particles, they're growing for a long time. They tend to be large. These are the early soot particles. And the soot particles that are nucleated later in the flame, they tend to be the smaller particles. So the soot particle size is really important for both the soot growth and the soot oxidation rates, and yet it's never a simple matter where they're all the same size or you even get a Gaussian distribution. It's a bimodal particle size. So there are three ways of tracking these particle sizes. The first one, the most accurate, but of course the most expensive, is Monte Carlo method, where you just pick a bunch of random sizes and track them through the flame and use them to statistically represent the entire population in the flame. If you're limited in computer time, as of course you always are, then you can use sectional methods. Now, instead of tracking hundreds or thousands of Monte Carlo particles, you can use about 50 size bins. And so you could separate these diameters into 50 bins and then populate the bins and watch how those bins propagate through the flame and how the populations in those bins pass through the flame. So those are sectional methods. And then that also is costly in computation. So the next simpler one is what's called the method of moments, where you can break this up into moments, about 3 to 6 moments, and then you have actually a transport equation for the moments of the soot sizes. So again, nucleation, not too complicated. Growth's not so complicated. The oxidation, I'll show on the next slide, isn't so bad for soot, but really it's understanding the particle size that's probably the most difficult part of modeling soot. And especially when you see the complex types of particle size distributions like this, that wouldn't fall out of very simple models of soot size. All right, then the last one here is the oxidation of soot. So you form this carbonation soot low in the flame, typically about halfway up the flame is when you transition from nucleation and growth to oxidation, although there's overlap throughout the flame. And then you have oxidation. Lots of people have looked at oxidation of soot, and they've identified the species that can oxidize the soot, and leading theories are now that the two main species that do this work, this oxidation work, are in order hydroxyl radical OH and molecular oxygen O2. Now, you also can have oxidation from O atom, it's very reactive, but at smaller concentrations, even water and carbon dioxide can oxidize soot. A lot of this work has been done from the coal, long ago research in coal, where they're looking at how coal burns and how carbon dioxide can actually oxidize coal. Often at the surface of a coal particle, you form carbon monoxide in smoldering. That forms carbon dioxide in a gaseous flame that then can go back to the surface and react further with the coal. But in soot, what dominates is hydroxyl radical and oxygen. And these are both shown in these two reactions. The reaction, first one, second one, hydroxyl radical, oxygen molecule, both forming carbon monoxide at the soot surface. So we did some work on this where we looked at lots of past publications and tried to separate out the oxidation rate from these different species, both in premix flames and diffusion flames. And we focused on studies that actually could measure accurately the hydroxyl radical, that could measure the O2 concentrations. And what we recommended, what we found seemed to correlate the data best, was for the OH oxidation to do a simple collision efficiency. What this says is that you look at the gas kinetics and the surface area, and 10% of the collisions between a hydroxyl radical and a soot particle, this collision efficiency 10, tells you that 10% of those collisions are an oxidative collision. So it's a very simple model. It scales with square root of temperature, just like the gas kinetic theory. And as long as you know the concentration of the hydroxyl radical, you can get the soot oxidation rate. There's a very simple model for oxidation rate by hydroxyl radical. And then for oxygen, it's a little more complicated, and it has an Arrhenius rate. It turns out that for oxygen oxidation, it's not as reactive, and so it really depends on the energy of the oxygen molecule colliding with soot, whether you have a reaction. And even though the leading model, here's a case where the old model isn't as good, 1962 doesn't do a very good job, even though it's still the most used Nagel-Strickland-Constable, we found that a slightly improved model was available as shown here. On the next slide, I'll show how that looks for these two models. This on the left is a plot of the predicted soot oxidation rate versus measured for the two leading models, Neo et al. For hydroxyl radical and Nagel-Strickland-Constable for oxygen. And you can see that these two models overpredict the soot oxidation. But with our models, and of course we had the benefit of all this data from all these 15 studies, turning the knobs, we're able to get a much better correlation between the predicted and the measured soot oxidation rates.
Sorry, Peter, this is fascinating. So the 62 model, they only use the triangle? So what's the data that they use in the original model?
Yeah, okay. So Neo et al., they wrote a model, and Neo et al. Is the pluses. So there's a plus here. It's a little bit hard to see where they are. I think, they use the data that's up here. And
and the fit is good. Yeah, okay.
Yeah, the fit is good enough. There's not much. There's many orders of magnitude here. Good question. All right. So if you're going to measure one thing in a flame, the easiest measurement, and to look at the soot behavior, the easiest measurement, and probably the most valuable one, is called the laminar smoke point. Now, it's a little confusing because laminar smoke point, it means two things. It means the length of the flame, and it means actually the flame itself, the condition of the flame. But a laminar smoke point, it's the condition and length of the incipient sooting of a diffusion flame. On this flame, I can't get up to the smoke point. I can adjust the flame height a little bit with this knob, but it won't let me get up to the smoke point. But if I were to make this flame 120 millimeters long, it would start to smoke. Now, it's hard to see that initial smoke with your eyes. We've done it with, dark field photography, white field photography, laser extinction, lots of ways to try to detect that soot. And it turns out the best way is just looking for the soot ears, they're also called the soot wings, where the annular region of the flame, the yellow emissions, are equally long as the center of the flame. So these are 6 different flames burning ethylene with these experiments upstairs and looking at the incipient sooting condition. So with different levels of dilution, you get different lengths of the smoke point, but these are what laminar smoke points look like. So they are the prevailing measure of fuel sooting tendency. A clean fuel like methane has a very long smoke point. In fact, methane probably doesn't even have a laminar smoke point. You have to go turbulent to get soot out of a methane flame. And some fuels like toluene, benzene have such short smoke points, lower than 10 millimeters. Now, a smoke point really tells you a lot about how that fuel behaves in terms of soot formation because it includes the nucleation of soot, the growth, and the oxidation of soot. It's really a competition of all 3 of these things. And again, a clean fuel has a long smoke point, dirty fuel has a short smoke point. Lots of numerical fire models now are starting to incorporate this into the models. So if you're burning fuels in a room like this, there are going to be fuels that burn relatively cleanly and fuels that burn not so well. And so having the smoke point behavior for each of these fuels is a useful part of a model. And we see that it's used now in FDS, from mist, and fire foam. And Chris Lautenberger has incorporated this into FDS. So the smoke point, if you want to have one property for a given fuel to indicate its sooting propensity, this is the one you'll want, the laminar smoke point. Okay. So what causes the smoke points? You know, there was, back in the day, there was a lot of debate between my advisor, Jerry Faith, and Irv Glassman at Princeton, that if you go on microgravity, you can't get a smoke point. Turns out my advisor was right. We did get smoke points in microgravity. I was on that airplane getting sick to find that. So, but they both had different arguments for their case, and those two they love to argue. And there are 3 different arguments. It turns out that they're all kind of tied one into the other and interlaced. So any of these 3 arguments is valid. So the first thing is that the smoke point happens when the soot temperature through radiation drops below about 1300 kelvins. What happens at this temperature is that the rates of soot oxidation fall off a cliff, drop down so fast that now the soot isn't oxidized and it gets emitted. That's valid theory. It seems to hold up. The second one is related to the radiative loss. If you look at the radiative loss fraction from laminar flames, the smoke points always seem to be associated with radiative fractions above 0.25. So blue flames, a flame like this that's not smoking probably has a radiative loss fraction about 0.2. If you go to acetylene and there's a lot of smoke, you can have radiative loss fractions of 0.5. And the cutoff seems to be a radiative loss fraction around 0.2 to 0.3. And then the third argument was about resonance time. This is one Irv Glassman at Princeton was using, arguing that microgravity flames wouldn't have a smoke point, that either you get sooting because the resonance time is so long that the flames are accelerating on Earth, and so you don't have time for oxidation, or that it's a ratio of the formation time divided by the oxidation time that controls it. So we did a study in 2012 where we looked at lots of smoke points and found that each different apparatus had a slightly different smoke point. And we were able to correlate them with just 1 or 2 knobs and do some kind of averaging so that for all these different 112 hydrocarbons, we were able to average across different facilities and put them all on the same scale and rate their laminar smoke points. Unfortunately, we don't have very many smoke points for solid fuels. FM Global has tried to do this, and as you know, it's very difficult to burn a solid fuel at a controlled flow rate the way that you can burn gaseous fuels or liquid fuels. So these are all for gases and liquids. Really, there's a valuable research that needs to be done to look at smoke points for solids that can feed into the computer models of the future. So let me talk a little bit about diagnostics and what can be done to measure soot. So The particle sizes typically we measure with transmission electron microscopy. What this means is that you generate a flame in the laboratory, take a TEM grid, electron microscope grid, these are 3 millimeter carbon discs, and rapidly insert them into a flame, usually with a pneumatic piston. It goes in and out very quickly, and by thermophoresis collects the soot. And we take it off gently with tweezers and go next door and look at it in the electron microscope. It's a nice measurement because it really just tells you what the soot morphology is, what those soot particles look like, what the surface area is. You can also get the particle sizes by light scattering, but this is often problematic. A lot of the times when people do light scattering measurements, depending on the wavelength and their method, they're actually giving you the equivalent spherical soot particle size, where what's more important is to know the size of the primary particles. And then you can get these also with mass spectrometry, which is a method used by Haiwang. You can also measure soot temperatures via pyrometry. Pyrometry is one of my favorite measurements, especially now with new cameras that are available. So we'll talk about that a little bit later. And then the other thing with soot is you want to be able to measure the concentration. What's the number density or the mass density of soot? And you can do this by shooting a laser beam through a flame. That's probably the easiest way. You can also look at the soot optical measurements, optical emissions, kind of like you do with the camera for soot pyrometry. And even in laser-induced incandescence, this is becoming quite popular, where you take a very powerful laser and you focus it and shoot it at soot particles and look at the incandescence from the soot particles. And from the decay back to temperature, you can get the soot concentrations. Let me start with soot temperature. And before I do that, let me make a little pitch for the value of soot as a temperature sensor. So the smallest thermocouple you can buy is about 25 microns. A typical human hair is maybe 75 microns. So these are small. If you want to drive a graduate student crazy, you tell them take this 25 micron thermocouple wire and you feed it through 100 millimeter piece of ceramic and they'll just go crazy. It's so thin and so fine and really hard to work with. But still, it's small, and that's what you want. You want small thermocouples if you're measuring high temperatures in flames because of the radiative corrections. But look at the advantage of soot particles. Even with the smallest available thermocouple from Omega, you're 3 orders of magnitude smaller with your soot particles. So what this means is that if you can read the temperature of your soot particles, then you have 3 orders of magnitude lower radiative correction. So you've got a much better indication of the gas temperature. And so that's the third bullet here, that the radiative loss in probes, whether it's a thermocouple or a soot particle, scale with the diameter. So if you can cut the diameter in half, you cut the radiative correction in half, you cut the uncertainty down, maybe not by a half, but by quite a lot. And if you can cut it by 3 orders of magnitude, that's a tremendous progress. Now, some people have, when I've talked about this, I'm going to use soot to measure my gas temperatures, they say, oh, what about, there's going to be slip, so it's not at the same temperature as gas. There's endothermic, exothermic reactions at the surface. And we've looked at that. And if you look at the thermal accommodation coefficient, which is a measure of the non-continuum mechanics of soot, it turns out that it's nearly unity. So those soot particles are indeed at the temperature of the gas. So let's use soot as a temperature sensor. And do some pyrometry. We did this with ethylene. Ethylene really is the canonical hydrocarbon for soot because it forms just enough, not too much. This is a 70 millimeter flame burning ethylene, and it's not beyond the smoke point. It oxidizes all the soot, so it's really a good fuel for this. Here it's just burning in air. I guess it's an 88 millimeter flame. And so we took pictures of this flame at lots of different wavelengths. We passed a red laser through it. This is a Heaney laser at 633 nanometers, and this is the black and white image we get from that. We used line filters of different wavelengths, and then we took pictures also in the visible. And from these different wavelengths, we can actually do ratio pyrometry and back out the soot temperatures. Now, these are line of sight measurements. So the flames are so steady. If you watch a video, or if you come in the lab and you see this flame, we've got it dialed in with the co-flow and the chimney and minimizing, blocking off the vents in the room so that that flame is as stable as a rock, doesn't move around. And that allows you to do your measurements over an extended period of time. It also allows you to do what's called an Abel transformation. When you look at this flame, looking through straight lines of sight, that line of sight is passing through low concentrations, low temperatures, high temperatures, and high concentrations. And so it's a projection, basically. You're taking a circular surface, a cylindrically symmetric surface, and in this case, if you pass a laser through it from the bottom to the top, you can see that the extinction of the laser is most on the center line, that's the longest path length through the flame, and least on the edges. And so the first step in doing any kind of measurements in an axisymmetric flame like this is to do what's called an Abel transform. A similar one you may have heard of is called onion peeling. If you think of this as similar to an onion with different shells of different temperatures and different soot concentrations. If you start from the outside and you find a soot concentration at that shell, then you move to the next layer in, you can peel away that onion layer, correct for that, and find the concentration working your way all the way into the center. But we prefer doing it with the Abel transform, just a mathematical trick, looking at the projection between XY space into radial space using this math here. The Abel projections, they're great on the edge of the flame, and as you go into the center, of course, you're peeling off all these layers, the error increases, and basically you have infinite error. You get a singularity at the origin. Of course, this isn't possible in fires, but this is kind of the state of art for measuring soot concentrations and soot temperatures in laminar flames. There are ways to do it in fires with probes or with actually measuring maybe less robust measurements, but getting an average soot concentration and average temperature. So when we did this, this is what we got. These are the soot pyrometry. These are the soot temperatures. They're the solid line contours here of the temperatures, and it's overlaid on the color image of the flame. We get temperatures in the range of 1600 to 1900 kelvins. Of course, as you'd expect, the temperatures are greatest near the base of the flame, where there's almost no radiation and high scalar dissipation rates between the reactions and diffusion of the fuel and the oxidizer, and then lower up high in the flame. So again, highest temperatures are low down near the low in the flame near the edges, lower temperatures up and toward the center of the flame. The spatial resolution with this technique, with this camera, is very good. 23 microns, just takes a tenth of a second to capture this image. Of course, it takes days of image processing to get these kinds of contours. And we estimate the uncertainty to be plus or minus 50 kelvins. A lot of it...
Peter, I think you're answering a question I wanted to ask you. Is this what explains the ears? You mentioned the ears, the soot ears.
Yeah, very good.
Is that? Wow.
So what explains the soot ears is that the streamlines that come in along the edges are very hot. And so you form a lot of soot on the edge of the flame. And that propagates all the way up. And so the first part of the soot to emit is on the edges of the flame. And then it's kind of isolated. When you get high, you get this thin layer of soot, and it quenches. It has a lot of radiation, and that's where the soot first comes out. Good question. All right, so the uncertainty is really hard to estimate. We estimate it plus or minus 50, but the precision is tremendous. These cameras are 14-bit, 16-bit precision, so you get very, very good precision. If you can take enough images, you get really beautiful statistics from these measurements. So to measure the laser extinction, we can get the concentrations in these flames two ways. One is by passing a laser through the flame, and one is just by looking at the radiative emissions. And this is a laser extinction by soot, where we take a Heaney laser and pass it. It turns out that the student found that instead of using a lens to decollimate the laser, it's better to take a vibrator with some frosted glass and actually cause the expansion of the beam this way. Goes to an off-axis parabola. Now we've got a collimated beam, passes through the flame, and focus that onto the camera lens here. And so basically get a shadow graph, a shadow view of the flame, which you can then calibrate and convert back to the soot volume fractions. And these are the results here. So I guess the key takeaway here is that soot volume fractions in flames like this are in the order of 10 parts per million. Those are volume, not mass fractions. So here we see that we go up to about 10 parts per million. And so again, it's concentrated on the annulus near the edges of the flame. We did this measurement both ways, by extinction with the laser on the right and by just emission, by taking a picture with the camera with no laser at all. And both methods agree quite well. If you look at them side by side, they're in pretty good agreement. So now I want to switch gears a little bit and talk about radiation, also known as thermal radiation. So radiation fires is basically heat transfer. You're looking at the heat transfer via electromagnetic waves, EMR, electromagnetic radiation. So all materials emit and absorb EMR. The only thing that doesn't is a vacuum, or something at 0 kelvins, which doesn't exist. And just as a little graphic, here's a picture of an electromagnetic wave. Of course, the electrical engineers love this kind of stuff. It's Maxwell's equation, Gauss theory, and a lot of what we do ties into that electrical engineering types of discipline. So for people who start out studying heat transfer and they learn conduction and convection, their intuition holds, they can solve these problems, the math is relatively simple, and then they get to radiation. When we teach this subject, we see them stumble. And even, everyone, I think, stumbles and has trouble with radiation. You never stop stumbling with radiation. And I think what's going on here is, as summarized in lots of good radiation books, I got this from Siegel and Howell, is that, as Arno mentioned yesterday, first of all, radiation can span long distances. So if you had a fire in this room, basically every wall in the room is communicating with every other wall at the speed of light. And with conduction and radiation, it doesn't happen. The molecules have to collide with each other. If you're interested in the heat transfer, you only need to look at the nearby vicinity to understand that heat transfer. So radiation goes over much longer distances. Secondly, the radiation doesn't scale. The rate of radiative heat transfer doesn't scale linearly with temperature difference, but it scales with temperature to the fourth. And so this becomes extremely important in fires and flames, because if you double the temperature, you have an order of magnitude increase in the radiation. Radiation requires no medium. So if you look at conduction and convection, you have to have molecules. You have to have a gas or a liquid or a solid for that to happen. That's not the case for radiation. It can pass through a vacuum, of course. And finally, the radiative properties of materials are very complex. So if you want to know about the heat transfer behavior of air, you can look up a thermal conductivity, the specific heat, the viscosity. All these properties are very well known at all different temperatures. And that's not true for radiative properties of materials, especially in flames. And especially when you get to these complex molecules, pHs, and soot, the radiative properties get really, really difficult. Okay, so it seems like a common theme of this summer school so far, and I hope it will continue, that radiation is a key factor in wildland fire spread, but not always. There are some cases, if you have fine fuels, it's not as important. But certainly, in looking at wildland fire spread, you want to understand what the radiative environment is. And I've got some citations here that talk about that. It's a very widely studied subject, but still not resolved, as shown here. And some by authors that are here at the summer school. So MODEST has this nice spectrum of electromagnetic radiation that's shown here. And of course, it goes from wavelengths of 0 to infinite wavelengths. But luckily for us, we don't really need that many. We're in thermal radiation for fires. Really, things only go from 1/10 of a micron up to 100 microns. This does span the visible range. It goes a little bit into infrared, and a little bit, it goes well into infrared and a little bit into the ultraviolet. But this is the area we're interested in. So luckily for us with flames, we don't have to worry about microwave radiation or X-rays, gamma rays. Really, it's close to the visible where things are happening for heat transfer. I have this equation here. Wavelength and wave number are used. Some papers report the results in wavelength, sometimes in wave numbers. So you need to do this conversion quite often when you're looking at this material. That's the spectrum we're interested in. This is the famous black body spectrum. It's a beautiful curve. It's so rich. There's so much in there. And even better than that is the fact that the whole thing is given by one simple equation. It's that very simple equation that gives you all of these curves and every other curve at every wavelength and every temperature. So in the middle here of the wavelength, you see this is the visible spectrum. And the most interesting curve here, I think, is the sun. Has the surface temperature equivalent of the temperature of 5777. Of course, we've evolved so that our eyes are most sensitive to the green. Green is the peak of the sun's radiation. If you're making night vision goggles and you want to see deer, on a night vision goggles, you probably want to focus on a wavelength around 8-10 microns to have the most sensitivity. Fires, the flames have temperatures in the range of 2,000 kelvins, peak temperatures of 1,500, 2,000 kelvins. But when people have looked at fires, they see something much lower because you get attenuation by soot and smoke and because of intermittency. So typically, fires have equivalent black body temperatures in the range of 1,000 kelvins. All this would suggest that the best way to look at fires is with long wavelength cameras, and there's a lot of good work that's been done there. But it turns out, even at 1,000 kelvins, you still do get good signal in the visible. You can see with your eyes things start to glow around 450 degrees C. All right, so this is meant to be kind of an introduction to radiation. That's the Planck's law, gives the equation of all these curves. The Stefan-Boltzmann law is what you get if you integrate this. There's no closed form solution to this, but it can be integrated numerically. And the total energy from a surface that's a black body is sigma t to the fourth. And then the third law that we rarely use in fire is the range displacement law. This just tells you the peak wavelength as a function of temperature. So for radiation, I want to split this part up into talking about radiation from surfaces, and especially I'm interested in smoldering surfaces. And then at the end, I'll switch over and talk about radiation from aerosols and gases, which is a more complicated story. So if you want to measure the temperature of a wall, if you want to go outside your house in the winter and find out where you may need more insulation around the windows, you can buy these infrared spot detectors. And it has a little red laser, so you kind of know where you're looking, and a trigger, you can pull it, and it'll tell you your temperature. You can use it to see if you have a fever, and you can use it to find heat leaks in your house. And so we know infrared is a good way to measure temperatures. Now, the trick with these devices is that they can have interference, they can have reflection, but also they need to know what the emissivity is. And so the ones that you buy, they assume emissivity of probably is about 0.9, but you can see errors from that, or if you try to use it on a day where there's a lot of background light. So these do measure radiation from surfaces, and then they attempt to convert that radiation back to some type of a temperature. Go up to 3,300 kelvins if you buy the more expensive ones. They won't work in a gaseous flame, but they do work pretty well for solids. Now, the technology is getting better and better. Instead of looking at just a spot, if you can do this with a spot, why not do it with an actual camera? So these are some infrared cameras that are available on the market today. On the upper right, you can see the Omega thermal image cameras. The firefighters call them TICs. They're about $1,000. This one isn't ruggedized for use in a fire, but for that price, you can get very low pixel resolution. And you can see here it's optimized to see somebody's heat of somebody's face, so in the mid-infrared range. There are two types of infrared imagers. Both are very useful, and both are used for fire on remote sensing. The first one are the thermal detectors. So the way a thermal detector works is it actually measures the temperature at each pixel. So pixels are dark, they're actually bolometers, they measure the resistance. It's hard to get past a megapixel, but with MEMS technology now, they can do this. You can get 1 million pixels, and you image your scene, and you wait. They're a little bit slow, but when the temperature is able to be measured, then you can convert that to an image. So it's a thermal detector. It actually measures the temperature. It seems like a primitive way to do imaging, but for the cost, that's really the best choice. Now, if cost isn't an object, isn't a concern, then what I recommend is this: for $100,000, you can buy a FLIR, the 6800. but you get only 1/3 of a megapixel. So it's nothing like the cameras we have even on the cheapest cell phone, but it is a quantum detector. It's not measuring temperature pixel by pixel. It's actually doing quantum conversion of photons to electrons. So these are fast, they're sensitive, but of course they're expensive. They do require cooling to avoid the noise at those levels, and cost up to $150,000. So these are expensive. I'm trying to interest you in the technology I'll present next, which is actually using a nice consumer-grade digital camera. Not only these cameras are expensive and have low pixel counts, but the lenses are expensive and have to be made out of exotic glasses. So these IR cameras are used a lot for remote imaging, especially on satellite. I show some of these satellite observation platforms here. But the problem is, or one problem with these, is that you just don't get very good resolution. Maybe 1 kilometer, 3 kilometers resolution. So if you're looking for spot fires, that's not going to tell you when there's a small fire starting if you have a 3 kilometer resolution. You just won't have the dynamic range available to pick out that fire. You have to be careful with infrared imaging. Between 5 and 8 microns, there's a lot of atmospheric attenuation from water and carbon dioxide, and so these generally get avoided. But what we've done in our lab, not having $100,000 to spend on the camera that we want, is to actually try to do this with color cameras. So this is the color camera we've been using. Nicolas Bouvet recommended this. This is a Sony RX10, and it's a really powerful camera. It comes with a built-in lens, but you can override a lot of the automatic features. And for $1,300, you get 14 bits, it's the bit depth, and 20 megapixels. We used it all the way zoomed out, focal length 24, and f number of 2.4. So the lens all the way open, and want as many photons as we can get, and zoomed all the way out. Every color camera has a filter array like this. It's called a Bayer filter array. You can see every pixel has a colored filter over it, either red, green, or blue. 50% of them are green because that's how our eyes respond. 50% of our rods and cones respond to green. But the nice thing is that for a camera like this, you get 20 megapixels, so it's 20 million pixels of red, green, and blue. Every pixel, you can figure out which pixel is red and which one's green. We don't bother with that. We just use the fact that at every pixel we get an intensity in the red, the green, and the blue. Sony has a nice interpolation where, even though it's maybe a red filter, it'll interpolate the surrounding green filters and determine what that red value should be. So it's 20 megapixels, but if you multiply by 3, because you get 3 colors, it's sort of a 60 megapixel camera compared to 1/3 of a megapixel for some of those infrared cameras. So what we're interested in doing with this camera is measuring the temperatures of soot, as I showed earlier in the soot section, and also measuring the temperatures of smoldering solids. In order to do those measurements, you need to calibrate the camera. And we have a very nice calibration tool upstairs, which is a black body furnace. And it's basically an electronic control box and a cavity, an oven basically, that can dial in temperatures and hold them between 600 and 1200 degrees C. So at 600, it's barely glowing, it's dim red. At 1200, it's yellow and quite bright. So what we do with this calibration technique is we dial in the temperature, and then we take pictures of the black body. It is really a black body. It's truly black. The emissivity is 0.98 on this device. And what you can see then is that the camera responds, and it responds in a nicely repeatable way to the temperature. So as we change the temperature here, we get intensity values that vary by 5 orders of magnitude. So it's tremendous dynamic range of the camera. To have 5 orders of magnitude variation in what you're measuring is really tremendous. Now, in order to get this, we have to adjust the time, we have to adjust the ISO in some cases, and the F number, but certainly the shutter time, and that all gets accounted for in what we're plotting here. So you can see the calibration works nicely for the red, the green, the blue, and the sum of all 3. It's a busy plot, but what I want to draw your attention to is that the scatter's small, and that you have 5 orders of magnitude. So if you want to do pyrometry with a single band, this is a really nice way to do it. But single band pyrometry has some problems in that you need to know the emissivity, just like you do with the infrared camera. and if there's smoke, it can throw off your measurement. And so there's some benefit to actually looking at the ratios and doing ratio pyrometry. Instead of just looking at one band, like red or green or blue, or adding them together, you actually take a ratio, the red and the green, or the red and the blue. So we take the same data then, and we'll show those ratios in the next plot, where the x-axis hasn't changed. This is still the temperature of our black body. And we look at the intensities of green-red, blue-green, and blue-red. And now we've lost a lot of that dynamic range. We no longer have 5 orders of magnitude, and that's quite a loss. It's a great loss in the signal-to-noise ratio. The measurements become more noisy, but there's also a great benefit in that you no longer need to know the emissivity of what you're looking at, whether it's soot or a solid surface. And if there's smoke in the way, that won't affect it. Even if the camera drifts a little bit, if the gain changes sometime, or you get dirt on your lens, it won't. We assume that it's immune to those kinds of changes if you look at ratio pyrometry. So really, in combustion and fire pyrometry, there kind of are 2 camps. There are the camps that do the wideband, single band pyrometry, and camps that do ratio pyrometry. And by doing both, we've actually found ways recently to put them both together and improve what we're able to understand. So here's this little table that talks a little bit about the key assumptions and the benefits of these. If you do single band pyrometry, you really need to know the emissivity of what you're looking at, like a smoldering surface, and you need to know the transmissivity, the tau, for the smoke. You also need to know the dwell time and image size if your image is smaller than 1 pixel. So those are the kind of assumptions you need to make with single band pyrometry. In ratio pyrometry, there's only one assumption here, is that the emissivity doesn't depend on wavelength. So it's I think a stronger assumption. It's a safer assumption. And then the key advantage of single band pyrometry, you get a great signal to noise ratio improvement, 18 times better. And for the ratio pyrometry, you don't have to assume anything about the emissivity, and you don't need to know about how long your fire or your flame has been there. And what we found is that we can combine these 2 ways, as I'll show. In one way, we can take the accuracy of the ratio pyrometry, but it's noisy, and account for that noise with the single band pyrometry, which isn't as accurate, but has very good precision. And the other way we can combine these 2 things, it's amazing to be able to get that much information just out of a color camera. The other way we can combine them is actually to measure the emissivity of the surface. So here's how we measure the emissivity of the surface. And even as last step, we can actually measure the heat flux pixel by pixel. So if you take a picture of a smoldering surface and you apply the black body equation, then you're going to measure the E on the left-hand side here, and if you back it out, you get an equivalent temperature if it were a single-band emitter at a relatively low temperature. This is a single-band temperature. It's a little bit lower because the emissivity isn't perfect unity. And then from the same picture, you can actually use the same equation and back out what the temperature would be for ratio pyrometry. And this, we believe, is the real temperature. If you do the ratio pyrometry, it doesn't depend on emissivity, isn't influenced by any smoke. And so this is what we believe is the true temperature of the smolder or the fire behind the smoke and the ash. And if we combine these 2 equations, again, the left side is the same in both cases, we can actually include the ratio pyrometry by single band and ratio to back out the emissivity of the surface. It turns out the values we're getting are reasonable with what people have predicted for this type of behavior. And then finally, we can take that emissivity and plug it into the power law equation, sigma T to the 4th, and get the heat flux pixel by pixel for smoldering fuels. And we hope that eventually this can be done also for flaming. Now, the current technology, the competing technology, is a heat flux gauge like this. This one's made by Medtherm. And they're wonderful. We all love them and hate them. We love them because it gives you a heat flux, and it's a real heat flux. We hate them because there's no absolute calibration. The only way to calibrate them is to travel back to NIST and put them side by side. In fact, Stas Stolirov did that recently and found out that there had been a mistake, and they had drifted by, I think it was 5%. So they also, if you overheat them, they still continue to give you readings, but the calibration is shifted. If the surface gets scratched or dirty, they can shift. So it's really not a very appealing way to measure heat flux. It only gives you heat flux at one. It's integrated over maybe 150 degrees. It gives you one value, a single point. It doesn't resolve your heat flux the way you can with the camera. And also, if you don't know how far away your object is, if you're close and far to different parts, it's hard to know what the individual heat fluxes are at different locations. So I have it in my sights to someday to use this pyrometry to be able to do a heat flux measurement better than MedTherm and to get it very quickly. These have a very slow response time at every pixel. So here's some of the early results we got for ember pyrometry with the color camera. By the way, these are two embers that are burning, one with the lights off, one with the lights on. These are 6 millimeters in diameter and 20 millimeters long. And we first looked at these images, like image A, the upper image, and we saw bright red areas. We figured that's the hot part. And then these black regions, and we didn't know, is that black because it's cold and it's not burning? Or is it black because it's burning underneath and that's ash that's attenuating the light? And it turns out that it's a little bit of both. When you turn the lights on, these two images are taken about a second apart. You can see that those black areas are actually white. So this is white ash, and that's slowing down the chemistry, so it's slowing down the heat release, but the temperatures are a little bit lower under those regions as well. So we did this ratio pyrometry, and we did the single band pyrometry to clean up the noise. And then in one shot, in a tenth of a second, we get 1 million pixels, 1 million realizations of temperatures on this smoldering ember that's shown here. So these are the temperatures on these scales, and then these are the emissivities that we measure with the technique that I showed before. And these are in the range, a little bit low, 0.5 to 1 on the emissivities and increasing with temperature. We also have a thermocouple in this image. So this image doesn't correspond to the images at the left, but if you put a very fine thermocouple onto this dowel that's burning, it has a hard time measuring the temperature, and it actually measures the temperature that's 230 degrees cold. So it quenches the ember, so you can see that it's blue in this image, and it has poor thermal contact. So everyone that's been measuring, at least for these wood embers, trying to measure the smolder temperature with thermocouples is likely to be 200 degrees colder than it should be. And this is a problematic for infrared imagers because that's how the infrared imagers are calibrated. They're calibrated with thermocouples. So even though in the color pyrometry you may not have as much signal to work with, we think that there's some benefits to doing the pyrometry this way that can get rid of the thermocouple and give you additional information like the heat flux and the emissivity, as well as the temperature, at nicely resolved like this. So lately we've been extending this to ember piles instead of looking at a single ember. Actually, we've been looking at airborne embers and getting reasonable results with that, and also for ember piles. This is work with Stas Delira that we've been doing on a UL-funded grant, where we actually did the same thing for an entire ember pile. And on the left, you see a color image of a pile, and on the right, the temperatures and the heat fluxes of that pile. And the fidelity is good, the results are good. It didn't agree with the heat flux gauge. And in this case, we actually believe the pyrometry result. We need to improve the measurements by moving the heat flux gauge farther away. Again, if the heat flux gauge is closer to some parts of the surface, it will be more responsive there. There's shape factor problem corrections that are really hard to make with the point measurement like that. So let me close out my part on radiation from solids by looking at another solid we've considered in flames, which is a thin filament. So if you want to measure temperatures in the flame, a great way to get it is with soot. Another nice way to get it is with a thermocouple. Thermocouples aren't so great because they only give a temperature at a point. But if you have a nice steady flame, you can translate it all around and eventually map out the whole flame, do the radiation correction. But what we found is that an advance on that, that works in some cases, is to measure the temperatures along an entire line. And so this is a thin filament. So it's silicon carbide, 15 microns, so it's very small, has an emissivity that's known of 0.88, and it glows in a flame, and you can do pyrometry on this. You can do either ratio pyrometry or wideband pyrometry, and this is wideband pyrometry. You want to measure the gas temperature, so there's a correction for this. Depends on the Nusselt number, the Peclet number. Scales with the diameter again here. This is the radiation correction that's performed. But you can see for this flame at these two heights, this one is a methane air flame, that the temperatures peak around 2,000 kelvins, and that you get a good agreement between the thermocouple measurements and the thin filament pyrometry. This may have a good application in fires, but not inside the flames. These filaments just aren't bright enough, they'll accumulate soot. But nearby turbulent flames and outside the flame, the response time is fast, radiation correction is relatively small, and the accuracy is quite good with thin filament pyrometry. Now, I want to switch gears, I think, one last time and talk about the more complicated aspect of radiation, which isn't radiation from surfaces, from solid surfaces, but radiation from absorbing, emitting, and scattering media. So something like a CO2 cloud, it's absorbing radiation, when it's hot, it's emitting radiation, it's scattering radiation, and so in order to understand the radiative transport, you have very complex math, to tackle these problems. As I mentioned before, every point in space in these radiation problems can interact with every other point at the speed of light. It turns out every different species, whether it's CO2, soot, water, has a different radiative behavior at every wavelength and every temperature. And so there's been lots of work to try to understand this for the species we have in flames and the temperatures we have in flames, but putting it all together and making a coherent model and then solving it in a reasonable amount of time with a computer is very difficult. So there are lots of what's called radiative transport equations of the type that's shown here. These are RTEs, and they're intimidating, to say the least. They're integral differential equations. Here's an example. So we've got different differential terms and integral terms. Basically what this says is that at each point in your fire, if you want to do radiative transport, you have light coming in, radiation going out, and that's got to be integrated over all space. And then you also have the behavior of that individual point itself as far as radiating and absorbing the light. So the math gets very hairy. Of course, to solve them, it needs to be simplified in a computer model. So radiation is a hard topic. Radiation of solid surfaces like a smoldering ember is hard. Radiation of an absorbing, emitting, and scattering gas like an aerosol is even harder. So to try to break it down for you as a summer school and make it, at least so you have some level of introduction to this, let's start with what's called the Schwarzschild equation. So in an absorbing gas or aerosol, the radiative intensity decreases with distance in an exponential decay given by this equation. The derivative intensity with position is equal to minus kappa times the intensity. So kappa here is the absorption coefficient. It doesn't help in radiation that they have three different names. It's also called the attenuation coefficient or the extinction coefficient. But this is the simplest. It's a radiative transport equation. You can get a similar equation for emission, but in this case, to make things easy, I'm going to show most of the math just for absorbing gas. If you integrate this, then you get a really famous equation that we all know from our heat transfer class. It's got so many different names: Beer equation, Lambert, Beer, Bouguer. So I just put them all together. But I over I0, this is the exponential decay of intensity with distance. And then this is equal to tau, which is the transmittance for a gas layer. Of course, the absorptivity has to add to the transmissivity to be 1. You have to conserve energy, so alpha plus tau equals 1. And now, this is the general equation over all wavelengths, but often, especially if you're going to do a detailed model, you want to write each equation in spectral form. So the kappa will not be a kappa here that's kind of assumed the same across all wavelengths, but it'll have a subscript of lambda and denote that kappa depends on the wavelength and the intensity depends on the wavelength. And this is part of the complexity with radiative transfer. So from this you can look at something that's called the optical depth or optical thickness, which is also unfortunately the same symbol, tau. It's not the transmittance, but it's tau. It's the attenuation coefficient k times the length, kappa times the length. And if you're much less than 1 in your tau, it's optically thin. Much greater than 1, and you're optically thick. And now let's look what happens for this in flames. So that's sort of considering maybe cold smoke or a layer of carbon dioxide where you're looking at the extinction of the light beam. In flames, it's a lot of the same math and some of the same equations, but now you're starting to emit power, radiative power, instead of absorb it. So we can take the same black body equation from before, sigma T to, so yeah, this black body equation multiplied by the emissivity, and this is the spectral radiative power coming from a flame. And here now the emissivity is again this 1 minus e to the kappa L, or emissivity, and this is the radiative power from the flame. So if you integrate this over all wavelength, so this will apply any given wavelength. If you know the temperature and the wavelength, and the admittance, this epsilon, you can find the spectral power. If you integrate across all wavelength, then you get to the sigma T to the fourth times the emissivity, this epsilon, where it's defined this way. So here you want to do the summation over all the radiating species. And this now, the kappa becomes what's called the Planck mean absorption coefficient. Instead of looking at the absorption coefficient for every different wavelength, you do an average weighting, appropriate weighting across all wavelengths, and you get what's called the Planck mean absorption coefficient. Now, it's a similar variable. It still looks like kappa, but in this case, it's multiplied by pressure times length, whereas before the kappa was just multiplied by the length. So if you work this out, and the equations in the math look a lot like the absorption equation, the Lambert-Beer law, you can solve these then in your CFD with three main absorption and radiation models. The most advanced and the most costly computationally is the line-by-line spectral model. So you look at every single wavelength across the radiative spectrum. And you do, this is called the statistical narrowband model, line by lines, SNB. Very expensive, can't be done for real fires or many real scenarios at all. And so what's typically done is to group the wavelengths into individual bands, and these are called wideband models, WB. So you look at the radiative transport for these wide bands. This too is expensive. And so what's being often used now for fires, as Arnaud Trouvé has been using recently, is the global models, like the weighted sum of gray gas. So as he mentioned yesterday, a reasonable assumption for the global radiative fraction is just to look at radiative fraction of the flame and apply that at each location in the flame. So for example, if you're burning methane, the radiative loss fraction is 15%. If you're burning acetylene, it's probably closer to 50%. But if you know what your fuel is in a flame in a model, you can apply that radiative heat loss at each location to really simplify the modeling and get away from complexity of soot radiation and soot formation and growth. So let me talk next a little bit about getting back to soot. So now we're combining the soot and the radiation, and this is a slide on aerosol scattering. So there are three types of light scattering from aerosols. You have the small particle regime, the medium, and the large. The small and the large regimes are relatively easy in terms of the math. The middle regime, the me, is quite complex, where different parts of the particle are interacting with other parts of the particle. Luckily for soot, it's small enough. The particle diameter is less than 1/10 of the wavelength of light, so you can use the Rayleigh scattering model, and it's quite simple. This is part of the advantage of using soot in pyrometry and measuring the concentrations of soots in flames. So to do soot extinction, what we do is we pass a laser beam, as I showed before, through a soot field, and you need to know the power of the incident laser beam and the power of the transmitted laser beam. And from these two, then, you get the I over I0, and you can solve for the soot volume fraction. Of course, you need to know the length, you know the path length. Now you have only one unknown in this equation, which is the kappa, the absorption coefficient. And luckily for soot, that absorption coefficient is directly related to the soot volume fraction by this equation. You need to know the wavelength, 632 nanometers for your red light. So everything is known here. Again, all you need to know for soot is how much is attenuated, what's I over I0, and how long is your path. And this directly and accurately can tell you the soot concentration along that path. So it has a complex index of refraction, so it's a real and imaginary part. The real tells you the scattering, the imaginary part tells you the absorption of the soot. But if you put all this in, you come out with a value of E of 0.26 for soot. Now there is a big caveat for soot. It's not like normal solids where the emissivity is independent of wavelength. For soot, the emissivity scales with 1 over the wavelength. So anytime you're doing ratio pyrometry for soot, you've got to factor that 1 over lambda in to your ratio pyrometry methods. So the last thing I want to talk about is a fun experiment that we do just upstairs every semester as part of the fire dynamics laboratory class. All of our undergraduates go through this, and it's a chance for them to see how smoke is characterized in fires. It's called the smoke chamber, ASTM E662. This is Nicholas Brondum. Back in COVID days, he was so dedicated coming out with a mask and doing these videos and getting the students excited about the smoke chamber. It's a box basically the size of, I don't know, an American dishwasher, where you heat a solid fuel, generate smoke, and measure the optical properties of the smoke. So it's nice because it's a sealed chamber, so you collect all the smoke that's formed. You expose only one surface of the fuel. It's a vertical light beam, so even if you have soot layers or smoke layers, it gives you an average, and it gives you nice quantitative measures of the soot behavior, the optical density. So this is what it looks like on the inside. There's a collimated beam. The students learn about incandescent lamps and focusing optics and light detection with a photodiode. It's an electric heater, resistance heater at 25 kilowatts per meter squared that irradiates a 75 by 75 millimeter specimen. In this case, we burn normally hardboard or plywood, and it generates a lot of smoke. We can do it either with or without a pilot, so we can do it in smoldering phase where you see they generate tons of smoke, or in flaming conditions where they generate much less smoke. And then they consider this with Boucher's law, Lemert beer, and look at the soot properties. So, in summary, I have, I guess, 3 bullets I want to say about soot and radiation that I hope you'll remember. Soot is formed only in flaming combustion, but lots of the media and lots of lay people will call other things soot, even dust and ash, but these are not soot. Second thing is that the complexity of soot is endless, but the best simple models really haven't changed that much. Some are 50 years old. That complex index of refraction from Seraphim is from, I think, 1960, and it's still the leading model. And then the small size of soot makes it really nice for pyrometry, that it's going to be always in equilibrium with the gas. Radiative emissions from fires can vary widely, 15 to 50%. It can dominate wildland fire spread rates depending on the scenario, and accurate measurements are very challenging. This is a bonfire from Northern Ireland. If anybody has a chance to watch this video, it collapses, and it's an amazing demonstration of radiation and soot all coming together, just an incredible collapse of I think it's a 40-meter high wooden structure. And with that, I am open for questions. Thank you.
We have a few minutes for questions. All right.
Yes.
Thank you very much for the talk.
Thank you.
Regarding the refractive index, I was wondering if that changes with the particle size. So within the flame, where you have different sizes along the flame length, this refractive index is supposed to change as well, right?
Nobody really knows. In fact, Seraphim, when he wrote the original paper, there was a typo in the paper. And later, 20 years later, people corrected the typo, and it changed the results a little bit. But now, actually, half the people, I think, if I remember it straight, people are still using the erroneous one that was published, and it seems to work okay. So there's still a lot that's not understood about how that behaves, but it doesn't seem to vary with the size of the soot particles. They're all in the Rayleigh limit, and that seems to apply there pretty well. That's a good question. I guess I can't fully answer your question. And there was another hand on the side, yes?
Yeah, thank you for the talk. I thought the pyrometry stuff was pretty cool, actually. My question was, is there any value, with regards to the soot stuff, is there any value in taking a solid fuel and pyrolyzing it, collecting that gas mixture, and then doing the techniques you did for gas, or do you think that's a crazy idea?
That's a great idea. That's a great idea. Stas Stolarov, he does some of that with his measurements in the lab, and I'm always interested in trying to do that to measure the smoke points. So can you measure the Lemmer smoke point for sawdust? So you pyrolyze the sawdust and pipe it into a burner, and then you can control the flow rate with the valve. I think it's a great idea, and people at FM Global have done some of that.
Nice. Thanks.
Thank you.
Thank you for the great presentation. On the question of using pyrometry on embers, do you think it'd be feasible to use them on embers mid-transport, i.e. firebrands, or do you think that considering the need to use a high focal length, you'd lose a lot of definition with the blurring? And
Yeah, okay, so the question's about firebrands, and we've done some of that work upstairs. We found that our first step was to do pyrometry of an ember that's stationary. And as a second step, instead of looking at an ember that's flying across the field of view, we actually held the ember steady and spun the camera. And so we could get streaks this way. So now we know the temperature, right? Because we had a second camera, we know the temperature of the ember, and we're spinning it by. And it turns out that it works, and it gave us the good temperatures. And there's a disadvantage that it's moving, right? But there's an advantage that it illuminates more pixels. So it's a little bit of a trade-off, and it turns out they kind of cancel out, and the accuracy is comparable. So we do think we can measure the temperatures of the firebrands. Now, some firebrands, Nicola has shown, are flaming, and some are smoldering. So once you get flaming, it wouldn't work. But for the smoldering embers, we believe it will work. Thank you.
But you asked when they're far away, right?
oh yeah, so I suppose the other question is the pyrometry method still viable if you're doing it, measuring from a distance?
That's a great question. Okay, if you're far away and you're doing single band methods, it's not accurate because the smaller it is, the smaller your signal, you'll think it's cooler, but it's the same temperature. But that's a nice advantage of the ratio pyrometry because you're doing the ratio of two temperatures. It shouldn't depend how many pixels large your object is. But the signal gets so weak at that point. Good question. Let me ask Arnaud to call on the...
Yeah, so let's call this side.
I have a question. Thank you for the intuitive talk. So, can the thin filament pyrometry be used for turbulent flame temperature measurement? So, how can we control the measurement uncertainty due to the proofing nature of the flame?
So the question's about thin filament pyrometry in a turbulent fire, and the response time isn't as fast as you might want, but so it depends on the level of the turbulence and the rate of change of the temperatures and the convective environment. I've only done it in laminar flames, but it should work, but of course it's not going to resolve the fastest motion of highest temperature change. Good question.
In the back.
Thank you for the presentation. For electron microscope measurements, you like capture the soot particle from the flame. How do you make sure that it's like a nascent soot particle, or if you capture an agglomerate, like can you distinguish between different nascent particles, or is it like all a clump?
That's a good question. So lots of times, if you're up high in the flame, everything's mature soot, and you'll see only the discarbonation soot. If you're down low in the flame, usually you just see oily particles. But somewhere in the middle, you shoot your sampler into the flame and look at it in the microscope. You can see both. Excuse me. You can see both, and they're pretty easy to distinguish because in one case it's a sphere that's relatively large and doesn't have high contrast. In one case it's solid, like a pearl necklace. That's a good question. Now, if you leave the beam focused for a long time on the oily particles, they start to boil and disintegrate and change while you're watching them. And that was very frustrating as a graduate student. You know, I was supposed to measure their diameters, and the diameter was changing. You had to work really quickly. Thank you.
Yes, please.
You mentioned optical diagnostics, and you also mentioned the thermophoretic deposition. But what about other sampling techniques, like aerosols, so you can see the particle size distribution? Has anybody tried this for fires?
Using what?
Like there are analyzers like differential mobility analyzers, SMPS, PEMS. I can name a few from different companies that are used for
Yes.
engines, for example.
Right.
Has anybody characterized particle size distribution from a fire instead of a laminar flame?
I guess I don't know. Hai Wang at Stanford does a lot of that type of work, but only in laminar flames that I've seen so far. I think it needs to be done for fires, certainly. Thank you.
Additional questions? Yes, please.
Thank you so much for your talk. I was curious about what sort of uncertainty you get with color pyrometry on your your temperature measurements of the firebrands in particular.
It's often hard to state uncertainties realistically.
Yeah.
And, you know, usually it's the end of the project, you've done all your measurements, you've done all your analysis, your plots are done, and then the reviewer's like, hey, we want a nice full uncertainty analysis.
Yes.
And it slows it down, it takes a long time.
Yeah.
And in the end, there's going to be some hand waving, it's not perfect. So
Right.
I think that flame temperatures, if you're measuring something, those temperatures are, 900, 1,000 C, the uncertainties are maybe plus or minus 25 C. And maybe that's optimistic. It's a little hard.
Yeah. Like, I mean, even with like the use of IR cameras in order to get temperatures, it's also there's hand waving and the
Yes.
emissivity and all that.
Yeah, it's
so,
all measurements.
Yeah.
That's right.
yeah.
So-
it's like looking at different sources and kind of like saying, like, oh no, they measured this with that, and
Right.
it's kind of circular in the way that there's no way to actually just get a temperature.
Right,
Yeah.
that's true. So we can cite the resolution, the precision of the measurement's just a fraction of a Kelvin,
Yeah.
but the total uncertainty is much harder to say. And usually for temperatures, we'll say plus or minus 25.
25 Celsius.
Yeah.
Which is remarkable. Yeah, okay.
Thank you.
All right, so in the interest of time, we have to stop here. Let's thank Peter again.